Now we go to the discussion of the Carnot engine, which is a theoretical cyclic process that will give the maximum efficiency of the heat engine between two reservoirs, hot and cold reservoir, between two temperature of the reservoir TH and TC. Okay, the name Carnot engine is to honor the Carnot, who is the engineer, the French engineer that gave us the expression of the maximum efficiency of the heat engine between the two temperature of the reservoir. In the Carnot cycle, the engine will work in 4 steps. That is, we may start at the first step here, that we have the gas. Assume that this is the ideal gas in the piston, and the gas is acting as the working substance for our engine. Okay, and this gas is in thermal contact with the hot reservoir at the higher temperature TH. We let the heat enter the system by the amount of QH and make the expansion, and here we let the expansion to be the isothermal expansion. That is, we keep the temperature of the gas at a constant temperature equal to the temperature of the hot reservoir. Okay, so it means that the system is in thermal contact with the hot reservoir all time in the equilibrium, in the thermal equilibrium with the hot reservoir on time. So the process is a reversible process, as we have discussed in the last section, that it is in the equilibrium all the time, but in this expansion is in equilibrium with the hot reservoir at the high temperature TH, and it perform the isothermal expansion. And after it expands to the maximum volume, we take away the hot reservoir and then seal the system to make the heat cannot enter or leave the system, and let the system expand further under the adiabatic process, that is, no heat enter or leave the system. In this process, you can see that in this expansion, since heat is 0, Q is 0 here, but the gas expands. So when the gas expands, it means that work done on the gas is negative. And since Q is 0, from the first law, we have that the internal energy of the system, the change of the internal energy of the system is negative. So it means that during this expansion, the temperature reduces. The temperature reduces since there is no heat enter or leave the system. So the internal energy decreases during this expansion, and since we say that the gas here, the gas inside is the ideal gas, so the internal energy depends only on the temperature. Okay, so we reduce the temperature, lower the temperature in this expansion. Okay, In the first step here, we have the temperature is constant because the gas in this step, the gas is in thermal equilibrium with the hot reservoir. T is a constant equal to Th, which is the temperature of hot reservoir. In this step, the temperature reduced because of the adiabatic expansion. Next, we put our system to the thermal contact with the environment or with the reservoir with the low temperature, Tc, and we let the system release the heat out to the environment, release the heat to the environment. Okay, so you can see that this is opposite to the first step. In the first step, the heat enter the system and make the isothermal expansion. Now, in this step, the heat leave the system and make the isothermal compression. In this step, the temperature keep constant equal to Tc, the low temperature of the whole reservoir. So the since T is a constant here, we must have that the change of the internal energy is 0. When the heat leaves the system, so it means that there is work done on the system and the gas is compressed. Okay, so we have the isothermal compression here, and once the volume of the gas it reach some value, we take away the low temperature reservoir and seal the system again and make the further compression under the adiabatic process, that is Q is equal to 0. Okay, Q is equal to 0. So in this step, you can see that there is work done on the system. We have that W is positive. Work done on the system is positive. So we have that the energy is positive. Okay. And since the gas in the system is the ideal gas, it means that when the internal energy increase, the temperature of the system will increase. The temperature of the system will increase. And once the temperature increase to that of the high temperature reservoir and the volume of the gas go back to the initial volume, we start the cycle again by putting the hot reservoir to the thermal contact with the system and let the heat enter the system again and repeat the cycle. So this is the cycle for the Carnot engine. Okay. We can also write down the Carnot cycle in the PV diagram. Here, this blue line is the isotherm. The isotherm is the line on the PV diagram that has the constant temperature. The above isotherm has a constant temperature of the TH, the temperature of the hot reservoir, and the lower isotherm is at the temperature of Tc, which is the temperature of the cold reservoir. So you can see that the first step, the system is expand. You can see that the volume increase and the system expand from the state A to the state B. The heat enter the system, okay, because we know that in this part of the process, in this part we have that W is negative, right, because the system do work to the environment. But since the process, during this process the temperature is a constant, so we have that delta E, the internal energy, is equal to 0. So we must have the heat enter the system to balance with the negative value of W and make the delta E equal to 0. Okay, so this is the first step in the Carnot cycle. And when the volume reaches at this point B, we take away the hot reservoir and let the system make a further expansion. And in this expansion, it is the adiabatic process. This is the adiabatic process. So during this process, Q is 0. W again still equal to still negative. It's like in the, because it is an expansion in the first process, as in the first process, that is we make a further expansion. But in the first process, it is the isothermal process. This is a this is an isothermal process. But here, this is the adiabatic process. And since Q is 0 and W is negative, it means that in this process, delta E I and T is negative. Delta E of the internal energy is negative. But the working substance is the ideal gas, so it means that the temperature reduces. The temperature reduces, so the temperature change from this state at this isotherm TH to the new temperature, this isotherm DT. Next, we put the cold reservoir to the thermal contact with the system. The cold reservoir is at the temperature Tc, the lower temperature, and this makes the system release the heat into the cold reservoir by the amount of Qc. And again, in this process, this is the isothermal process. delta E int is equal to 0 if Q is negative because heat leaves the system, right? The heat leaves the system. We must have that W is positive. So there is a work done on the system. It means that the system is compressed. The volume decreases because there is a work done on the system during the isothermal part here. So we can see that in this step, the volume of the system will decrease. And once the volume decreases to the volume at the point D, we take away the reservoir, the low temperature reservoir, and we let the system do further compression from D back to the original or the initial state A. During this step, we seal the system so there is no heat in or out. So it means that Q is equal to 0 during this process. So it is a adiabatic process. So Q is 0, and you can see that W is positive because there is work done on the system. So it means that delta E int is positive. The energy of the system, the internal energy of the system increase. So it means that the temperature, because the working substance is the ideal gas, and the temperature and the internal energy depend only on the temperature. So we have that in this step, the temperature increase, and when the temperature and the temperature, the volume, and the pressure change back to the initial state. So we complete the cycle. And we repeat the cycle again. In one cycle, you can see that the work done by the engine, the work that the engine gives to us, is equal to the area under the curve, to this area. Okay, so this is what we got from the Carnot cycle, that work between two reservoirs, the high temperature reservoir and the low temperature reservoir. From the Carnot process or Carnot cycle that we have discussed, Carnot state that no real heat engine operating between two energy reservoirs, that is between the higher temperature TH and lower temperature TC, can be more efficient than a Carnot engine operating between the same two reservoirs. This means that if you have the heat engine with the hot reservoir of TH at the temperature TH, and it gives you the heat of QH to your engine, and your engine gives the work W in G and leave the heat QH. QC to the cold reservoir at the temperature Tc. Carnot state that the efficiency of your engine will always less than the efficiency of Carnot engine. Okay, the efficiency of your engine for the real engine will always less than, or if it is the ideal engine, is equal to the Carnot engine, but it cannot greater. Here it means that your engine has to work with the same pair of TH and TC. If your engine works with the same pair of TH and TC to that of the Carnot engine, the efficiency of your heat engine will less than or as much as equal to the efficiency of the Carnot engine. In the real situation, the Carnot engine is not of that practical use, because all process in the Carnot engine is a reversible process, which, as we have discussed, have to be very slow. So Carnot engine may give the maximum efficiency of the energy, but it will not give the maximum value for the power, because the energy will be the work done from the system will be really slow. So the power output can be really slow. We use Carnot engine for the theoretical analysis only, not for the real application. But in the real engine, we try to make the engine have as much efficiency as the Carnot engine as possible.